Okay, so balancing this redox reaction. Remember that these additional species that you're observing, this guy, for example, this guy, and this guy, aren't necessary to include in this reaction. They've been included so that we don't have things with charges. They basically exist there as charge balance. But as far as this reaction is concerned, they're just spectator ions, so they're just sort of charge placeholders that keep it balanced out. They're not actually exchanging electrons, and as a result, you can sort of think they're not actually involved in the actual reaction. So the first thing that we have to figure out is which of these species are going to be experiencing a change in oxidation number, or which ones are actually involved in the sharing or exchange of electrons. Looking for not oxygen, not hydrogen, not polyatomics that stick together, mainly looking for elements in the middle of the periodic table that can be flexible and change numbers. But anything that appears as an element like this is almost for sure going to be part of it, because if it's in compound, it has a non-zero oxidation number, and if it's as an element, it has a zero oxidation number, so there's certainly going to be a change there. So chlorine is the easiest element to identify here. Sodium has a charge of +1 when it's in a compound, and so the chlorine will be -1. So we have here is chlorine -1 going to chlorine as it exists as an element or with an oxidation state of 0. I include the 2 on the diatomic chlorine because it has to exist in that ratio in the molecule, so I might as well include it at this point in that ratio because I need that when I get to the final answer, and it's going to help me get the number of electrons that are actually required to create that diatomic chlorine. But it should be balanced in the half reaction, so if I have Cl2, then I should have 2 Cl to balance that out, right? I need 2 chlorines. I had -2 and I went up to 0, so if I want to balance the charge, that means I need 2 electrons on that side. Now sulfur is another atom that is typically involved in oxidation state changes. And I just want to say one more time why I'm not worried about sulfur in this example. Do you notice that everywhere where there is a sulfur, it's part of the polyatomic ion sulfate? Sulfate has a charge of SO2-. So the sulfur in each of those, since the oxygen is the same, the sulfur must be sitting at the same oxidation state to lead to that same total of -2 all the time. So because I see it remain as a unit or as a set thing, I can count on the fact that it's not going to be the thing that's involved in a change in oxidation state. If I had a sulfate and then it changed to a sulfite or sulfur trioxide or something like that, then it would definitely be something of concern. But since it stays in the exact same situation or the exact same combination throughout all of the balancing, it must, as a result, have the same oxidation state in that polyatomic ion at all times. So the other atom then is the manganese. Here, these oxygens, there are 4 of them for a total charge of -8. This potassium has a +1, so the remaining charge on the manganese is +7. Here I have it with the sulfate, and again I'm going to treat sulfate as if it's one whole thing with the charge of -2. That's really from a -8 and a +6 for that sulfur, but overall its charge is -2, which means that that is +2. +7 going to +2 must have absorbed 5 electrons. So when I look at my number of electrons that are produced in my oxidation number increasing, so that's the oxidation, and the number of electrons that are absorbed in my reduction, I can see 2 and 5, and obviously you can't have 2 electrons being produced and then expect 5 to be available for the next reaction. Those 2 have to agree. So the lowest common multiple for these things, if I can't get anything lower than 10, so I'll multiply this guy by 5. That makes that 10, that 5, and that 10. And if I multiply this guy by 2, That makes that 10, that 2, and that 2. So this manganese corresponds with this manganese in the equation, so I'll put my 2 there. This manganese corresponds with this manganese, so I'll put my 2 there. And this chlorine minus goes with the sodium, so I'll put my 10 there. And this chlorine is this element, so I'll put my 5 there. Now I've got a lot going on, and I've got to start looking at those additional species, so I'm going to erase everything that isn't the coefficients that I just put on so I can get a clearer look at what I'm doing. Okay, so these coefficients set the electron balance or the electron exchange, and so we're going to think of them as fixed. If something worked out where we had something that just couldn't balance and we had to multiply them all by 2 or something like that and say 20 electrons in and 20 electrons out, that would be okay, but we can't get them out of ratio with each other. So if we sort of view them as fixed, the vast majority of the time it'll work itself out. I only have one thing left to balance on this side of the equation, so I'm going to start looking for stuff to balance over here. And I'm looking at my things that are set, and here I see I have potassium with my KMnO4, and that's the only spot I have potassium on this side. It has 2, so that tells me that this guy, which is the only one on my right-hand side that has potassium, must have a coefficient of 1. And while we don't need to write it down, I'll write it down and underline it so that I realize that I've thought about it and it's fixed at that number. Next I see hydrogens here and hydrogens here, and sulfates here and sulfates all over the place over here. Actually, I'm looking at this guy right here. I see sodium. There's 10 of them, and there's only one spot where there's sodium over here, so if I can deal with things that only occur once, that's the best thing to start with. 10 sodiums, that means I need 5 sodiums right there. 10 and 5. And so now I have everything set on this side except for the H2O, so I better go over and deal with my sulfates on this side since all the sulfates are fixed, and then I'll be able to go back and look at my water to finish the hydrogens. So 5 sulfates here, 2 sulfates here, so a total of 7. 8 sulfates when I include that one, so that means I need 8 sulfuric acids to get those 8 sulfates. And 8 times 2 at hydrogen gives me 16 hydrogens, and the last thing to balance here is the hydrogens here, so I'll put an 8 in there, and I have 16 hydrogens. So everything should be in balance, but as a check, I'll look at oxygen and just make sure that the oxygens on the left-hand side match the oxygens on the right-hand side, and if they're good, then I'm going to assume I'm balanced correctly. 2 times 4, I have 8 from that molecule. 8 times 4 is 32 from that molecule, for a total of 40 on the left-hand side. 1 times 4 plus 8 plus 8 plus 5 times 4, which will work out to be 20. So 4 plus 8 plus 8 plus 20 works out to 40 on the right-hand side. And so since the left-hand side and the right-hand side are balanced with one another, we're going to assume that this is correct.